Okay, Bismillah ar-Rahman ar-Rahim. Welcome back, ya shabab, to the class. Before I get started, I want to tell you that I finished grading quiz for sections number 6, and I am gonna finish number 7 soon, inshallah. What else? I'm gonna post the solution once I finish grading. And of course, you probably received the news about the midterm. So the university this time were a little bit more reasonable than the other time, in the sense that we were asked to, if possible, reduce the load on the midterm since it is online, but try to find some good ways not to overload you with the quizzes. Okay, so the number of quizzes that we are going to have is still going to be the same, but we are discussing now with the coordinator what is what are we going to do to make them, the midterm just being, it's going to be held on the same day, 16th of March at 7 p.m. All students will attend from all sections, will have the same problems, everything. But we're trying to think about a way to reduce the load, the amount of, grades on that midterm, and put something else. So we'll see what is that something else, okay? But for us, this is it. I mean, you should not expect that we're gonna do anything else. So it's not like we're gonna give you extra assignments, or we'll see how are we gonna split the midterm into two things, and we'll tell you soon, inshallah, about the arrangement. Okay. I think that's it. Today, hopefully, ya shabab, we will finish chapter number 13. So let me remind you about this problem that we had last time. We actually went through all of this. If you recall, for this problem, we found the transverse pitch angle. Then we found the velocity, pitch line velocity. In order to find the pitch line velocity, you need the pitch diameter, and to get the pitch diameter, okay, it is equals to the number of teeth divided by the normal, what is it? The transverse diametral pitch, which is this, obtained from this equation. So that's our guy. And then when we divide the number of teeth over here, 18 divided by PT, we get dp, the pitch diameter, which is used to find the velocity. Once we find the velocity, we can find the tangential load, which is the transmitted load. And once we find the transmitted load, the other two forces can easily be determined. And this one is the resultant force. Now, what I told you last time is we now know all of these. The distances are known. And we know even this distance, which is, this is the pitch diameter over 2, the radius. So we know this distance as well. Now, what is important here is that you can visually, and I explained to you the difference between this problem and the one for helical gear. The one for helical gear, you had the z-axis like here, or the x-axis, and then the z-axis here, and then this is the y-axis. So this is z, this is y, this is x, and the point where the two gear get engaged, okay, is somewhere in this plane. So when you have forces like this, all right, or actually I put two forces against each other. So when you have forces like this, then what happened? You need, for example, to this force to move it to here, and then have this distance in order to multiply it to get the moment, for example, right? Then you need to transfer this force to here and then get another moment there, and so on. So that's why it was three-dimensional in nature. We have three components of each force, and we needed, to do it in a vector notation. Now, in this problem, what do we have? The whole, if you go back, you will see that, you see that this is the gear, this is the other one, the pinion, and this is the point where they get engaged, they mate. And this is all in this plane, happening in the same plane. Yeah, there is nothing, we need to, yes, there is a force, which is the transmitted load coming into the other plane, but that's it. The point of action is acting in the red one, and the tangential or the transmitted load is acting along the blue one, which is horizontal. This one is vertical. But since that point is in line with the red plane, it becomes a little bit easier to analyze it without the need for vector analysis, if you think so. Now, so what is it? Let me just highlight this problem, and because it is more or less similar to the other one, I don't think I should spend too much time in detail like what I did before. But here it says that we have the three forces determined. Look at them. This is WR in the negative Y direction. This is WA in the negative X direction. And this is the WT, the transmitted load. Now, we assume that bearing reaction, these are the bearing reactions. So bearing A, don't forget that bearing A was decided from the problem, from the question, to be the one which is going to handle the thrust load. And that's why it has one radial direction force, which is along the y-axis. There is another one, which is along the z-axis. And then the axial load is acting this way. The other bearing has what? Has this one, only two, which are radial. The resultant of them is going to be somewhere here in the middle. So what did we do this time? Instead of going into this vectors, we said, okay, by inspection, we know that the only force which is resisting the axial load over there is the radial load. I mean, the axial thrust, which is going to be taken by the bearing. So simply, WFAX, which is this force, is the same as this one. So we got rid of one. This is one reaction now is known. So it says that this is the same. Now, we can take the moment about the z-axis. And look, if we take the moment about the z-axis, you can actually see clearly, ya shabab. So we take the moment about the z-axis at this point. So all of these are not going to make any moment, all right? And we can see that this force, for example, the WA, if you look at it, it has a perpendicular distance with respect to this, and it will make rotation about the z-axis, right? This force will not. Why? This one actually, the WT is going to make a rotation about the y-axis, not the z-axis, right? And if you look, you will see that WR also going to make a rotation about the z-axis in kind of the opposite sense to WA. Why? Because this force, if you look, this is now its perpendicular distance. So this is WR multiplied by this yellow line, and it will make that rotation about the Z. There is one more, which is what? Which is Fy at location bearing B, which is also gonna have this blue distance as a perpendicular distance, and it is going to make a rotation along that direction. So I can go ahead and say, well, this is now the WR, which is now look, WR is gonna rotate this way. If you do the rotation with the right hand rule, you will see that the thumb is gonna point toward the negative Z. So that moment is negative. So it is there, -17 multiplied by this distance, which is 3 plus 10. Okay, and we have then the 23 over there, which is WA. That WA is going to make a positive. So that WA is multiplied only by this little distance. That's how much arm it has to make the rotation about Z. And then we have, of course, FPY also making a positive rotation about Z. And its distance is only 10 inches multiplied by the force, which is equals to 0. Clearly, what is the unknown over here? One unknown. So we got rid of FPY. Good. So it seems handy. Now, if you sum the forces along, let me clean it up because it got busy over here. So the forces along the Y direction. So this is Y direction, this is Y direction, and this is Y direction. Now, this is known. We just determined this. This is unknown. So I can find what, ya shabab? I can find, what is it? I can find F A along the Y direction, which is 3.1 pound force. Good. Any question? Okay. So next is to take the moment about the y-axis. We just mentioned that. So let me clean this up again, and let's see what are the forces that make moment. Definitely WT. So WT, if you think of it, it's a vector, right? You can move it down. So if you move WT over there, then its distance is here, and it is going to make a rotation in the positive Y, right? So that's right. So this is a rotation which is going to go up in the Y direction, so it is positive. And what else? We have, let me make it in green. We have FBZ, which is going to be multiplied by this distance to make a rotation in the negative direction. So the FZ is going to go like this. Yeah, no, this is, so it is down, right? And clearly these are the only forces that making moment about Y. So what do we have? We have, remember that WT is 40.4. So this is the 40.4. And this one, I think I flipped them. Did I? Yeah, I did. Look, WT is here. When WT is rotating, it will make the rotation along this direction. Yeah. So it is acting actually downward. And the green one is going to make it positive, which is this way. So that's why over here we have this is negative and this one is positive. So if we do this, we can see that we have only one unknown, which is this, and we got it. So we determine the unknowns now. If you want to find the torque, you can easily find it because it is basically going to be equal to this force by the distance over there, which is equivalent to the torque. But as far as the reaction acting on the bearing, you actually found all of them. So as I told you earlier in the last class, if you felt more comfortable with the vector, then this is how you do it. Now, my advice to you is that you don't leave it for chance, Shabab. You don't leave it for comfort, whether you are comfortable to use the vector notation or the scalar one. I think you should be ready for both. You don't know what are you gonna face. I'm not talking about the exam. I mean everything. You are a mechanical engineer and you should know how to handle this. So my recommendation to you is to go home and probably take a chance to solve this alone, this one, and see if you can arrive to the same result. When you make mistake, it means you have weakness. Just track that weakness. See why that weakness is there. What is the concept that you missed? This is a weak point. Is it because you did not understand something? Is it because your understanding of something is wrong? Or is it because you forget something? Right? You forgot. I don't know, for whatever reason. So this will will help you understand better. Okay. Now, the last part of this chapter is the worm gear. Give me 1 second, Yeshara. I think this is not something wrong with my cloud. This is not the other file, Yeshara, wasn't updated, so I have to upload it again. So let me see, where are we here? Still the same. All right, so we'll come back. Now, we are going to talk about the last part, which is the force analysis for worm gear. Now, worm gear, ya shabab, is different than other gears. It is similar in the sense that, again, we have a tangential force, like a transmitted load, and then we have a radial, and we have an axial load. There is no doubt about it. And if you look over here, okay, you will see that this is our friend, the resultant force, coming at an angle in a 3D space, okay? And remember that, by the way, when I say in a 3-dimensional space, what I mean is that that force may be coming from this angle all the way to that angle. You see that? So it has a projection in X, Y, and Z. So what happened is we look here and we see that the concept here is that if we neglect friction, and the idea here is, I'm pretty sure you will come and say, whoa, what? Friction? We never talked about friction. And the first confusion that will happen, that cause, of confusion to you, they say, oh my God, did we forget to include friction? So we spent like 3 weeks, I don't know, 2 weeks, and we never talked about it. And did we do something wrong? Well, don't worry, we didn't. Okay? And the reason is coming soon. But for now, to establish the background here, or the ground for you to understand what are we going to do, we are splitting this into X, Y, and Z component. And again, if we take that total vector W, and then we project it into X and Y and Z, just like when I showed you with the cube, then the angle, where phi n is the pressure angle, normal pressure angle, and lambda is the lead angle, if you remember, then we can actually know what are the forces in each component, X and Y and Z. Okay, now what happens is that there is Wy. If you look at Wy, where is Wy shown? This is the Wy. Wy is called the separating load, or the radial force. And it tends basically like to separate the two from each other. And we have the tangential force on the warm gear, which is Wx, and Wz on the gear, assuming that this is a 90 degrees. Okay, engagement. Now, this is just the general that we assume that there is one force and we have X and Y and Z. Then what do? We usually indicate, as you remember before, that the small guy is the worm, which is like a screw. And the circular one is the gear. So we are going to make a unified distinction between both of them when we use W for the worm and G for the gear. Good. So if you want to know the forces acting on the worm, then it is W sub WT, which is the opposite on the gear, which is the same as WX. And we have WWR, WWA, which is for the worm. And they are, of course, opposite to what happens to the gear. That's something we know from equilibrium. And they are corresponding. So the tangential is on the X, the radial is on the Y, which is the separation load, and WA is the axial load, which is acting along the Z direction. Okay, now we are going to make a convention here. So whenever you have a problem of a gear and a worm gear, and you have the choice to decide about the directions, which is X and Y and Z, then we are gonna always try our best to align the gear axis to the X direction and the worm axis to the Z direction. You get that? So it's just a convention that we are going to try our best to always have it. Okay, so the gear axis is always parallel to the X, and the worm is always parallel to the Z. And hopefully, ya shabab, if you have any problem around, and you have been given the diagram, hopefully it is following this convention. Okay. Now, what is important is this. This is the difference. In the past 2 weeks, we talked about spur gear, we talked about helical gear, we talked about bevel gear, right? And we never mentioned the concept of friction. And there was a reason for this. First, if we talk about a spur gear, we said that the point of contact is actually a line. It's a line. It's not a point. The reason is because the tooth has a face, right? And the other one, when it come and get engaged with it, you know, the conjugate action, the envolute, if you still remember it, we said that there is a strip over here, which is going to be moving as the point of contact move along the envolute profile. But we said, oh, the helical gear is very special in the sense that the point of contact is actually a point. It's not a line. So it's a point which moves. So it is even more efficient in the sense of friction. When you have only one point, wrapping another one point is better than when you have a straight line wrapping over a straight line. Now, in here, with this, look what I'm saying. I want you to read. Just look at the screen. It says in spur gear motion, one tooth relative to the mating tooth is the motion of one tooth with respect to the other when they are mating together is primarily rolling. So they roll. And if you remember from dynamics, you said rolling without, without slipping. And when we say rolling without slipping, we put the friction and we assume that the point of contact has an instantaneous center of zero velocity and so on. So this is rolling. And in contrast, ya shabab, the relative velocity or motion between the worm and the worm gear is a pure sliding. So they are actually sliding against each other. They are not in contact. They don't come contact each other and move together. They are always, one of them is sliding over the other. That sliding motion makes a friction a big deal. عشان كذا يا شباب, if you have your steering wheel for the car bump broken, the bump, كلكم تعرفوها. That's it, you are doomed. It will be so hard if you just think about it to just steer the wheel. Now, I am not saying that this is primarily to the friction, but you have a bump, a dedicated bump with a lot of oil going to the steering mechanism just to take care of that friction. Because in a steering mechanism, we know that steering rod that you hold with your hand, it is connected with a worm and then the worm with a gear. And that's how you have it. So for that reason, we need to include the friction. That's the only new thing here with worm and worm gear. So the friction force, if we all call it WF, then it is going to be, we know that it is equals to the friction coefficient by the load, like the normal load. And if we wanted to include the friction term, it is going to be this. It is going to affect the axial force. So we will add F friction multiplied by cosine lambda and minus F sine friction lambda, sine lambda, minus F the friction coefficient by sine lambda. These are the only two parts that are going to be affected, the only two forces that are going to be affected by the friction force. So just to tell you that there is the friction force WF, which is F, the friction coefficient by the force, is equal to this equation. You can use this. So this is the tangential load on the gear And these are the pressure angle, this is the lead angle, and this is the friction coefficient. Okay, there is also, you can use these other equation to have a relation between the tangential force on the worm and the tangential force on the gear. These kind of equations, you may not use them for a problem, but they become handy a lot when you design. It's just, design is such, weird thing that maybe that force will help you determine the other, and then you can size your problem. So whenever friction comes, the efficiency concept comes. How much are you gonna lose? So the efficiency, which is eta over here, is equal to the W, the force on the tangential force of the worm without the friction, divided by the tangential force of the worm with the friction, which is expressed in terms of this equation. It can be shown that that relation, that ratio, is actually coming purely from the angles, which is cosine phi n minus f tan lambda divided by cosine phi n plus f cotan lambda. Okay, that's a cotangent. Okay, so this is some lead angles in degrees, and this is the efficiency. As you see, for gear set with a friction coefficient equals 2.05. This is just an example. So when we said that there is a sliding, then logically we want to know what is this sliding velocity. We'll see that the sliding velocity is very important. So the sliding velocity Vs, okay, is equals to the velocity, the pitch line velocity of the worm divided by cosine lambda. Okay, another thing, if you know the sliding velocity and you know the type of material in general, if you have high quality material, ya shabab, is like nicely finished steel or copper or zinc compared to casted one. Casting, we know it causes roughness and so on. So you have these two curves in general, okay? And if you know what is the sliding velocity, and you know that your material is good, high quality, then you should go to curve A, and then you will know what is the coefficient of friction F. So F is either given to you or you should determine it from here. To determine it, you need to know the sliding velocity. So you need to know the kinematics, the speed and whatever. And you need to know what is the material. Of course, if there is nothing mentioned to you about the material, you can always assume it, okay? It's a good finish, nice finish, or whatever. Now, so within the limited time that we have, let's go over this problem. We have a two-tooth right-hand worm, it's just a worm that transmits 1 horsepower, that's the power, at 1,200 revolution per minute with a 30. So this is 2 teeth, and we have 30 teeth on the gear. So this is the worm, this is the gear. Okay, the gear has a transverse diametral pitch of 6 inches, of 6 teeth, per inch, and a face width of 1 inch. The worm has a pitch diameter of 2 inches and a face width of 2.5. The normal pressure angle which is phi n, is 14.5 degrees. The material and quality of the gearing to be used are such that the curve B is used, which means it is not high quality. we need to find the axial pitch, the center distance, the lead, and the lead angle. And then we want to figure out what are the forces, again, acting on the bearing. So if we look, this is the diagram that was provided in this problem. What we see here, this is the RBM, and it is going on a counterclockwise, all right? Counterclockwise fashion. Now, if you recall, we said we always want the arrangement such that the worm is aligned along the Z direction. This is the Z. And we said that the gear should always be aligned along the x-axis. Good. Now, the dimensions are given to us over here. So we know the sizes. And as you see, this is bearing B, this is bearing A. And I just want to tell you that when this guy, this is a right hand. This is an actual right hand worm and worm gear. And it's a little bit confusing. I mean, when this guy rotates in this direction, okay, it's like it will be visually as if these teeth are going on the backward. And when that happens, it's like they are pushing this along this line, which is the gear. And that would cause the gear to rotate in this direction. So similarly, if this one rotates this way, then this is going to rotate that way. Okay. Now, I know we don't have time, so let me at least cover a little bit of this. When we studied worm gear in the introduction a few sections ago, we said that the axial pitch is the same as the transverse direction pitch, and that is equals to pi over P. So what is P over here, ya shabab? Do you remember? P is the transverse diametral pitch. So if you take pi divided by P, which is pi divided by 6, you will know what is the transverse, which is equals to the axial pitch. Now, then we also know that the diameter, the pitch diameter for the gear is equal to the number of teeth divided by P, okay, capital P. So since we know what is capital P, which is 6, and we know the number of teeth, which is 30, it was given to us, then we can divide 30 by 6 and we get 5, which is the diameter, the pitch diameter for the gear. Now, in the next class, I'm gonna continue. So basically, we're gonna find the center, and because it was asked, it says what is the center distance. Then we'll find the lead. This is also from the section for the worm. We'll have the lead angle. All of these were requested from us. Now, these are equations. They were given to us. Now, if you recall, the velocity for the worm is the pitch line velocity of the worm. We can find it. Once we find the pitch line velocity of the worm, we can find the pitch line velocity for the gear as well. And then from this, the velocity of the worm, and from the lead angle, we can find the sliding velocity. Once we find the sliding velocity, we can go ahead and find the friction. Once we find the friction, and we use the transmitted load equation, knowing the power as well as the velocity, we can get WT. Once we find WT, we can find WR and WA. And once we find those forces, okay, we can do the analysis again for the bearing. Okay, I'm gonna stop here. This is not gonna take too much from next class, and then we will start the new chapter.